In this video, we are going to demonstrate the delta modulation and demodulation. So delta modulation is nothing but it is a 1-bit data transmission, right? 1-bit digital data transmission, right? So already you know what is PCM. So PCM is nothing but pulse code modulation, right? PCM is nothing but pulse code modulation, and it involves three stages of process: sampling, quantization, and encoding, right? So in case of PCM, right, if suppose the first sample value is 0.6 in the sense, then it will be quantized into 1. After that, this 1 will be encoded as 000001, right? So encoded, the normal conventional PCM, we are going to make use of 8 number of bits for encoding, right? Similarly, suppose the next sample value is 0.7 in the sense, then again this 0.7 will be converted into 1, right? Next it will be converted into next higher level, that is 1, right? It is round off into 1. Next this 1, again the same value will be encoded as 000001. So in this case also, that data, encoder data will be 4 zeros and 301, right? Yes. So now what we infer from this process here, whatever may be the different number of samples, right, the same we are going to transmit the same encoder data, right? That is, redundant information or repeated information will be transmitted, right? So it just wastes the bandwidth. So bandwidth and power are wasted in case of conventional PCM, right? Why? In the sense, because even though we have different samples at the input, we are going to transmit the same encoded data, right, in case of conventional PCM. So in case of conventional PCM, power and bandwidth both are wasted. So to overcome this process, we are going for delta modulation. So delta modulation is nothing but 1-bit digital transmission. 1-bit digital transmission. So here actually what we are going to do is, we are going to compare the adjacent samples, right? So the first sample value is 0.6 and next sample value is 0.7. We are going to compare this greater than threshold in the sense, we are going to transmit logic 1. Right, we are going to transmit logic 1. I suppose the threshold, the difference value is less than the threshold in the sense, we are going to transmit logic 0. Right. So in this way, we are going to transmit only 1-bit information instead of 8 bits. Right. Instead of 8 bits, we are going to transmit only 1-bit information. So that is why in delta modulation, bandwidth and power both are saved. Right. Both are saved. So this is the connection of delta modulation, right? Delta modulation. So initially the input signal, modulating signal is applied. Modulating signal is applied to the comparator, and the sampling pulse is applied to the sampler, right? Sampler. And at the feedback, right? In feedback path we have the integrator circuit, right? Integrator circuit, and we have the step size adjustment, right? Step size adjustment for delta modulation, because in delta modulation we have two different types of errors, that is slope overload distortion and granular noise, right? So to avoid those errors, right, we can adjust the step size. We can adjust the step size with the help of this control. Okay. Now we are going to measure the input signal, right? So CRO is connected at the input. So this is the input signal, right? This is the input analog signal that we are going to apply at the input of delta modulation. So here we need to take the amplitude as well as time period, right? Amplitude as well as time period. Yes. Now I am going to connect the CRO at the input of sampler, right? Because we are going to observe the sampling pulse waveform. So CRO is connected at this pin, right? And after this, we will be getting sampling pulse like this, right? Sampling pulse like this. So this is the sampling pulse which is used for sampling process in delta modulation, right? So here also we have to mark the on period and the off period as well as the amplitude, right? Amplitude of the on and off pulse. Now we are going to, so this is the delta modulation output, right? Here actually we will be having single bit data, right? Single bit, either it is logic 1 or logic 0, right? Logic 1 and logic 0 based on the difference between the adjacent samples, right? Sometimes the value will be 1 and sometimes the value is 0, right? So in this way you will be getting the delta modulated output. This blue color waveform is delta modulated output, and similarly integrated output, right? We are going to take the integrated output, right? So this is the integrated output, and this waveform, this output is connected to the CRO, right? Again, now we are going to compare these two signals, right? integrated output and delta modulated output, right? So whenever charging, right, during the charging period we'll be having more on time, and during discharge time we'll be having off time, right? So this is integrated and delta modulated output. So what we infer from this waveform, what we infer from this waveform here, there is a slope overload distortion, right? There is slope overload distortion. That is why this charging period some of the peaks are missed out, right? Slope overload distortion. Slope overload distortion in the sense, already I said in delta modulation there are two errors. One is delta slope overload distortion, another one is granular noise, right? Granular noise. So this is the slope overload distortion, example for slope overload distortion, right? In this case, the input signal has the steepest variation, whereas the staircase waveform, that is the integrated output, is less, right? It is not able to follow the input signal. That is why most of the cases the delta modulated output will be off, that is 0, right? So this is nothing but slope overload distortion. Now we can overcome this slope overload distortion by adjusting the step size value, right? By adjusting the step size value. Here actually we have one provision, that is step size control, right? This step size control, if we are going to adjust the step size control, there is a changes in the slope overload distortion, right? So in this case we don't have any slope overload distortion. Here there is no slope overload distortion because we have both charging as well as discharging waveform, and similarly in delta modulated output we have on pulse as well as off pulse, right? On and off pulses. So all the inputs in all the charging periods are take over by the delta modulation, and delta modulated output will be on in that time, right? So here the slope overload distortion is eliminated, right? This is the model graph. Now we are going to demodulate the original information, right? So for that, the delta modulator output is applied to the demodulated input, right? So after demodulation we will be getting the staircase waveform, that is reconstructed waveform. That reconstructed waveform will be applied to the low pass filter. Here actually we are going to make use of 6th order low pass filter, that is there are 6 RC sections inside the low pass filter, right? So the number of filter order is increased, in the sense then we will be getting smoothened waveform, right? So at the output of low pass filter we will be getting the reconstructed output. Now CRO is connected at the output of low pass filter, right? And that waveform, right? This blue color waveform is reconstructed waveform, and this is the yellow color waveform is input waveform, right? So both signals are same, right? With a slight time difference, right? Slight time difference, right? So in this way we are going to demodulate the original information. For the model graph, right? Message signal, one is message signal, then integrated output, then corresponding delta modulated output, then reconstructed signal, right? So for all these waveforms you have to mark the amplitude as well as time period from the CRO, right? So from the CRO you are going to note down amplitude value as well as time period value for all the graphs, and you can plot the respective graphs, right? So this is what the delta modulation and the demodulation.